Alright, hello everyone. This is just to clarify a few little things about significant figures discussed today. Let me start with the Google Slides, this one on your screen. Two guys are standing here, and that if you have a measuring tool like that, with marks 2, 1, and 0, likely you will only be doing an estimate. One possible estimate could be, oh, this guy is about 2 meters tall. Yes? Okay, say we have the same device, only that we consider dividing the interval between 1 and 2 into 10 equal parts, and the device therefore should look like this. Your estimate is likely to be closer to the actual value. They call that precision. A reading with this device having this calibration here could be 1.7 or 1.8. Mind you, this is the same as the meter stick in the laboratory or your ruler at home. When we read and use the centimeter unit, we can have one figure that we are certain, plus one last figure, which is our estimate. See, 1.7 or 1.8 in this case. 1, we are sure that is more than 1, but we have an estimate that it must have this 7 or 8, all right, in our number. Now imagine that in this device we considered another interval and divided that into 10 equal parts again. Then our measurement is even closer to an actual value, or better say, more precise as compared to the others. We can record in this case 1.75 or 1.76. Repeating the idea over and over again, having 10 equal partitions between another within a selected interval would give us more precise measure or another decimal place and so on. However, we cannot do this forever, isn't it? There will come a point where two line indicators are too close, giving us no way to divide into 10 equal parts anymore. Precision then stops there. This means that what we have is basically just an estimate of a quantity or length in the case of our examples here. Alright, you still remember the last statement that we had? There is no way we can have an exact measure of a quantity. It is always an estimate due to the limitations of measuring devices. The only numbers in physics that may be regarded as exact or equivalently have infinite number of significant figures are those numbers that came from definitions, like the 1 half and 2 in the kinetic energy equals 1 half mv squared. Those numbers are regarded as exact or having infinite number of significant figures. This means that we need to be very careful when dealing with numbers taken from measuring devices and need to add few consideration to those you already learned from a mathematics class. I'll do some examples in operating with this later. Meantime, let's try to see first the significant figures in the following numbers or quantities. Okay, here we have three significant figures in each quantity. Remember that all non-zero digits are significant. Now, in the case of zeros, it may or may not be counted as significant figure depending on its purpose in the number. In some resources, whether these zeros are significant or not depends on where these zeros are in that particular number. Let us consider these examples, 0.12 and 0.12. Okay, you see that? Obviously, these are not significant. I know that you guys even write 0.12 instead of 0.12, and this 0.12 here is just being written as 12. These kind of zeros are not significant, meaning that in these two examples, we both have two significant figures only. Now, if the zeros are located between two significant figures, the zeros are significant. Consider these examples. The 1 and 2 there are significant figures, and the zeros there are between two significant figures, meaning those zeros are considered significant. So in these cases, in these examples, we have three significant figures in each of them. We also have these so-called trailing zeros. These are the zeros to the right of a decimal point in at least one significant digit. These are significant figures too. Examples here, 12.0, 1.20, 0.120, like that. All non-zero digits are significant. So these ones and twos here are significant. Now these zeros at the right of the decimal point and at least one significant digit are trailing zeros. And trailing zeros are significant. We have three significant figures here in this example. Now, one thing that usually confuses people are numbers like these: 120, 1000. Sometimes people would say three significant figures in 120. Sometimes people would argue that no, only two significant figures. I would say, guys, that the correct answers depend on what you originally have. Imagine this. I have 1.2 grams. Obviously, this measurement has two significant figures, yes? Now, say your teacher asks you to convert that into centigram. What will be the answer? In centigram, this 1.2 grams is 120 centigrams. Now the question is, with only conversion that has taken place, we did not use a more precise measurement, would the number of significant figure change? No. After conversion, the number of significant figures must be maintained. So the number 120, based on what I just told, must have two significant figures only, rather than three significant figures that you were saying before. Similarly, this 1000 here. Imagine that this is expressed in millimeter. Imagine that you have at first 1 meter. In 1 meter, there is only one significant figure. And then you converted that into millimeters, giving you 1000 millimeters equivalent to 1 meter, is it? If this is the case, we need to maintain the number of significant figures of the original number. 1000 millimeter is therefore having one significant figure only. Okay, take note, guys. Saying that 120 has three significant figures rather than two significant figures, which I just explained earlier, may also be correct sometimes, depending in the case or scenario. I'll go through the idea on our next meeting next week, okay? For the worksheet that I embedded here, just use the rules I mentioned above. I'll clarify the issue in the next set of examples next meeting, okay? Alright, let's proceed to how we operate with numbers having different significant figures. Let's start with addition and subtraction. I have here 1.11 plus 1.1. In your calculator, you will see that answer is 2.21. But do you think it is logical to accept that in a physics class? The 1.11 has a better precision than the 1.1. We can say that these two numbers were taken from two devices with different precision, isn't it? One is more precise than the other. And see the result of calculation in your calculator. It is following the precision of the first number, which is illogical as it looks like it even brought the number to a higher precision without changing the device by only operating with addition. Let me remind you guys that calculator is not a god. We must not take all that you are seeing on the calculator's display. Your result in addition and subtraction must follow the degree of precision of the less precise number. So in this case, the answer should be 2.2 and not 2.21, which is too much of a precision. Do this same concept of practicality when subtracting numbers here. Calculator will display 1.135 here. This is of the same degree of precision as the first number, but this number exceeds the other number's degree of precision, meaning that reporting the result as 1.135 is illogical as well. Round the result off such that the precision is the same as that number, which is less precise. It should be 1.14. Now, when multiplying or dividing numbers taken from measuring devices, we have to do the same logic as explained. However, in this case, we write the result such that it has the same number of significant figures as the number with the least significant figures. Mind you, when adding and subtracting, we consider following the decimal places of the number that is having the least precise measurement, while in multiplication, we follow the number of significant figures of the one that has the least significant figures among the numbers we combine. Do not interchange the idea. Let me give you an example. 2.27 times 3.2. Calculator will give us 7.264. What's the problem with this? You see, only by multiplying, the result exceeds the number of significant figures of both the numbers you combine. 2.27 has two significant figures, 3.2 has two significant figures. Is it logical to have a result with 4 significant figures like that? Obviously not. Increasing the number of significant figures by just multiplying things or dividing things is very impractical. We have to deal with this by following the number of significant figures of the number with lesser significant figure. The answer should be 7.3 only, following the number of significant figures of the number 3.2. Now another here, 11.5 divided by 2.3. Using calculator, this will give us 5 as the final answer. Isn't there a problem with this one, guys? You see, we have 3 significant figures in the first number and 2 significant figures in the second, and our result has only 1. We are losing something here. This must be wrong. To correct this, the answer should be 5.0, following the number of the significant figures of the one with lesser number of significant figures among those numbers you combine. Alright, I hope that this clarifies a few things. In O-level physics, during Cambridge International exams, you will be allowed to use calculators. But remember that calculator is not a god. Don't just copy the result in the display of the calculator. Write your final answer using the ideas I mentioned earlier. Okay guys? Bye.